In the previous two videos, we've seen how to define the directional derivative of a function at a point in the direction of a given vector. And we've seen how to compute the directional derivative by defining the gradient vector and using the dot product formula. In this video, we're going to look at some properties of the directional derivatives that we've developed in those videos. So to get started, I want to recall a basic fact of dot products, since the directional derivative can be computed in terms of dot products. So one way to compute the dot product of a vector A times a vector V was to first take the magnitude of A, multiply it by the magnitude of B, and then multiply it by the cosine of theta, where theta is the smaller angle between the vectors. And so this is a basic property of dot products that we saw before. So if we take this particular property and apply it to our directional derivative, which we know is the gradient vector of f dot our unit vector u that gives our direction, then this, by the property above, would be the magnitude of the gradient vector multiplied by the magnitude of u times the cosine of theta, theta being the angle between. Of course, the unit vector u has a magnitude of 1. So this is just going to be the magnitude of the gradient vector multiplied by cosine of theta. All right, so this is another way we can define the directional derivative, is namely that it's the magnitude of the gradient vector at the point multiplied by the cosine of the angle between the gradient vector and the direction of that we are interested in. Now, this is not a good formula to compute the directional derivative, because that we would have to somehow know that angle between the vectors first, and that's a lot more work to do than just to take the dot product with the gradient with the vector u. But because we know a lot about cosine of theta, we know how that function behaves, we can actually come up with some properties of the directional derivatives by thinking of the directional derivative in this particular way. So using this interpretation of the directional derivative involving the cosine of the angle between the gradient vector and the unit vector u, we can come up with three basic facts about the directional derivative, about rates of increases of our function, which can be important in contexts, in different contexts. So the first fact that we can come up with is the following. So we can say that the greatest rate of increase of our function f at our point AB will occur when angle theta is equal to 0. Right? And that's because we know that cosine of 0 is equal to 1. Right? So if we look at that formula for the directional derivative that is in terms of cosine theta, we have the magnitude of the gradient vector times that cosine. If I want to find the largest positive number that could be, that will occur when cosine of theta is as large as possible, which is 1. The only way we can get cosine of theta to be 1 is when theta is equal to 0. And so this particular angle is going to give us the direction that gives us the greatest rate of increase. So if we want to say this a different way, this will occur when u points in the same direction of the gradient vector. At that point. Right? So what we want to do, if we're at a particular point on this graph and we want to determine the direction that we needed to go to find the greatest rate of increase, this fact tells us what to do. This fact tells us to compute the gradient vector at that point and look in that direction. and that will be the direction that gives us the greatest rate of increase. Now, in this particular direction, not only do we know that, but we know exactly what our directional derivative is going to be. Right? Using that formula we just derived, this is going to be the magnitude of the gradient vector at that point multiplied by cosine of 0 degrees or 0 radians, and of course that's equal to 0. That's equal to 1. And so not only do we know our direction, but that rate of increase is just going to be the magnitude of the gradient. Now we can flip basically everything here on its head, and we'll get our fact 2. And so in fact 1, we were talking about the greatest rate of increase. We can also talk about the greatest rate of decrease. So in which direction is this function going to decrease at the largest rate? Okay. And so this is going to occur when the angle theta between our vectors is equal to pi. And that's because sine or cosine of pi is equal to -1. Okay. So again, we're thinking of it kind of the same way. How can we make this directional derivative very large but negative? And the answer is we want cosine to be negative and as large as possible. So the largest negative number in the sense of being magnitude being largest is -1. And so that occurs when theta is equal to pi. Right? And so what this tells us is that if we want the greatest rate of decrease, this will occur when u points in the opposite direction of the gradient vector. So if we want the greatest rate of increase, we compute the gradient, we look in that direction. If we want the greatest rate of decrease, we find the gradient vector, and we look in the exact opposite direction of that vector. Right? And again, in this case, it's pretty quick to compute the value of the directional derivative. Right? We're going to have the magnitude of the gradient vector multiplied by cosine of pi. And so we just get the negative of the gradient vector. The negative of the magnitude of the gradient vector in this case. So for our third fact, we've seen where the rate of increase is greatest, where the rate of decrease is greatest. And the other thing that we might care about is when is the rate of change equal to 0? So the rate of change is going to be 0 when theta equals pi over 2. Right? And again, that follows from the obvious fact that cosine of pi over 2 is equal to 0. Right? And so the other way to think about this is that it will occur when u points in a direction orthogonal to the gradient. And so along with our first two facts, these three facts, we can answer questions about these things without actually doing much computation. All we really need to do is look at find the gradient vector and compute its magnitude. So let's look at the following example. Let's say we are given the function f of xy equal to sine of x plus y squared. Okay. And so what we want to do for this particular function is we want to find the direction and value of the greatest rate of increase greatest rate of decrease and of no change, the direction of no change from the point negative 1, 1. So as we just identified the three properties a moment ago, the key to all of this is to compute the gradient vector at the point negative 1, 1. All right, so to do that, we'll start by just computing the gradient vector as a function, as a vector function. So the derivative of this with respect to x will simply be cosine of x plus y squared. And the derivative of this function with respect to y will be cosine of x plus y squared. But then we have to multiply by the derivative of x plus y squared, which is 2y. So it's going to be 2y cosine x plus y squared. Right. So this is our gradient vector in general. We want the value of the gradient at the point negative 1, 1. And so we're going to get the cosine of 0, negative 1 plus 1. And we're going to get 2 times 1 cosine of 0. And so this will be the vector 1, 2. And at this point, we might as well go ahead and just compute the magnitude of this vector while we're here. So this will be the square root of 1 squared plus 2 squared. And so that'll be the square root of 5. That's the magnitude of our gradient vector. Okay? And so now we can answer all of these questions with these particular values. Okay. So first thing I want is the direction and value of the greatest rate of increase. Okay. Well, we know the direction from our properties that we saw a little bit ago. We know the direction is in the direction of the gradient vector. And that gradient vector, that direction is 1, 2. And the value of that greatest rate of increase we know is the magnitude of the gradient vector, which is 5. Okay. If I want to talk about the greatest rate of decrease, the direction of the greatest rate of decrease is the opposite direction of the gradient vector. So that would be negative 1, negative 2. Remember, to change direction of the vector to make it the opposite direction, we just scale it by a negative 1. And the value of that greatest rate of decrease is the negative of the magnitude. So in this case, negative square root 5. Right? And if I want to the direction where there's no change, no change in increase or decrease, then what we need to find a vector that is orthogonal to our gradient vector. Now our gradient vector here, 1, 2, is a very simple vector. And so it's actually, various ways to do this, but in this one we can just do it by inspection. If I need to find a vector orthogonal to 1, 2, one option would be negative 2, 1. All right, and just kind of think about what would I need the coordinates to be so that when I take the dot product with 1, 2, I get 0. And so certainly if I take the dot product of this vector with the vector 1, 2, I will definitely get 0. And another vector that would work would be 2, negative 1. That's the opposite direction of these. Right? And so any vector in one of these directions would work. Right. So we want, there are two vectors. There's only two directions that are orthogonal to a given vector, and they're going to be opposites of each other. And these are the two directions. If we wanted unit vectors, we could easily scale this by square root of 5 to make them unit vectors. But to just indicate the direction, any vector can be used at this point. The last thing we want to talk about is some basic properties of the gradient vector itself. As I said, we introduced the gradient vector in these series of videos in order to compute the directional derivative of a function. This will not be its only use. It will come back later on in a couple of different ways, and we'll revisit it. And at various times, we're going to need to compute the gradient of sort of complicated functions, ones involving products and quotients and so on. And so what we're going to do now is just come up or develop a few properties of the gradient vector so that if I have to compute the gradient later on of something complicated, we can rely on these properties in order to do that. Most of these properties should be familiar to you. The gradient vector is just a vector consisting of derivatives, and so it makes sense intuitively that this should satisfy a lot of the standard derivative rules. Right, so for example, if I took the gradient of a function f plus or minus another function g, so I have two functions that I'm adding or subtracting together, this is going to be the gradient of f plus or minus the gradient of g. Right, so the gradient of a sum or difference is just the sum or difference of the gradient vectors themselves. Same thing with a scalar multiplication. If I have a scalar k multiplied by a function f, and I take the gradient of that, this is just going to be the scalar k times the gradient of f. Okay. We also need to look at what happens if I take the gradient of a product of f times g. Right, so it turns out that this satisfies what we would typically think of as sort of a product rule. So it's going to be the function f times the gradient of g, and we're going to add to that g times the gradient of f. Right? And so this works pretty much like it looks much like the product rule for derivatives, except instead of taking the derivative, we're taking the gradient of the two vectors f and g. Right? And the last one here is what happens if we want the gradient of a quotient, f divided by g. What we get here is g times the gradient of f minus f times the gradient of g all over g squared. And again, this is provided that g is not equal to 0. And of course, if g is 0, this makes no sense to begin with, so why would we even be considering the gradient? But this looks, of course, just like the quotient rule for derivatives. And so it's quite easy to remember the product and quotient rules here, since they're exactly what you've seen in the past. So just an example to look at these properties. Let's say we wanted to determine the gradient vector of the function f given by the formula x squared minus xy cubed, all divided by x squared plus y squared. Now, of course, we could compute this. We could compute the partial derivative of x and the partial derivative of y using the quotient rule for standard derivatives. But these properties of gradients we just discussed provide an alternative way to do this. So if I want to compute the gradient of f of xy, this is just the gradient of the function x squared minus xy cubed all over x squared plus y squared. Okay, so we have the gradient of a quotient, so we're going to apply the quotient rule that we just looked at. And so that says we're going to take the denominator, in this case x squared plus y squared, multiply that by the gradient of the numerator. Right? The numerator, the partial with respect to x, is going to be 2x minus y cubed. The partial with respect to y is going to be negative 3xy squared. And we're going to subtract from that the numerator, x squared minus xy cubed, multiplied by the gradient vector of the denominator, which is going to be 2x comma 2y. Right? The partials of the denominator with respect to x and y are quite easy. And we're going to divide this by the denominator squared. And now this is just an exercise in vector arithmetic, vector algebra. And so we're going to have a vector here in the first component. It's going to be x squared plus y squared times 2x minus y cubed. That's from our first vector. And we're going to subtract from that x squared minus xy cubed times 2x. And that'll all be over x squared plus y squared quantity squared. And our second component, it seems I'll have to write a little bit smaller, will be x squared plus y squared times negative 3xy squared minus x squared minus xy cubed times 2y all over x squared plus y squared squared. Right? So apologies for that running over and for the kind of double line writing here on the second component. But I think everyone should know what I'm doing here. And if one wanted to, you could go through and simplify all of this, but it's really at this point just a tedious algebra problem. Typically, when we have the gradient, we want to evaluate this at a particular value of a particular point for x and y. And so this form is certainly good enough to substitute in values for x and y. And so this gives us an alternative way of computing this gradient. It allows individual derivatives to be done a little bit quicker than it would be if we had to compute the quotient rule for both the partial of x and the partial of y. We can sort of do the quotient rule in one step as a gradient quotient rule, and then the actual derivatives that we compute are just derivatives of the numerator and denominator individually. So it's a little bit simpler in that respect. Right? But like I said at the beginning of this portion of this video, these properties of gradients will be useful from time to time when we encounter the gradient in the future.